derivatives. Derivatives is kind of going to be essentially the meat of calculus that we're going to do the most. We're going to do derivatives and we're going to do integration. Integration is backwards derivatives. Okay? If you looked ahead, you're like, oh my gosh, there's so much going on. The nice thing is that derivatives will have rules. Like they'll have the power rule, which you'll see on Monday, which you'll hate me, which is okay. Okay? Then they have the quotient rule. You have the product rule. Okay? They have specific patterns in which you need to do them. This is the type of stuff I'm talking about at the beginning of the year, that once you guys get to that point, a small mistake can make a page of work go down the drain. Okay, so it has to be very detailed, very organized, and just making sure you're crossing your I's, or crossing your T's, dotting your I's, all that kind of thing. Okay? Just a second. All right, so derivatives are defined by limits. So that's the good news. We're just doing limits, okay, but we're going to learn rules of how to do them. Okay, so today we are doing the drawn out derivatives. Then we're going to get into the rules. That's what I was talking about. You're going to be upset with me, but that, like I said, that's fine. So in this section, we understand, we've already seen this, f of a plus h minus f of a over h as h approaches 0 occurs for slopes of tangent lines. Section 1.5, we saw this type of limit also arises in computing velocities. In fact, it occurs as a rate of change in all branches of science and engineering. Since this type of limit occurs so widely, we give it a special name and notation. The derivative of a function of f at a number a is this, which we're familiar with. So really, we're not learning anything different. Derivatives are the limit as h approaches 0 of that function. We have some shortcuts and some rules that are going to help us. That's the hint. This right here, I want you to notice that. See that tick? That means derivative. If I say I want f apostrophe or whatever, tick of x, that means I want the derivative of f of x. Okay, so that's a notation you want to remember. If there's two of them, what do you think that means? Two derivatives, exactly, the second derivative, and we'll keep using that notation throughout the year. Okay, any questions? We're good? Okay, alternatively, this one still works as well. Okay, remember we had the two forms? We still have the two forms. We have the f of x minus f of a over x minus a as x approaches a. That's also a derivative. Okay, so you haven't learned anything new yet. All you learned is that derivatives are defined by limits. Okay, and we know limits, right? That's what's on the test tomorrow. Hopefully we know that. Okay, so example 1. 2x squared minus 5x plus 6. We want to find f derivative of 4. So you can pick either way you want. I'm going to give you some time to try this. You should know how to do this. You should know how to do this for tomorrow. Okay, I'll pause the video. So if you're using the, again, I'm going to use the limits h goes to 0. So I have f prime, they call it f prime, FYI. F prime of 4. Limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. So that's going to be a little bit ugly here, but I got to put the 4 plus h in there and square that out. So that's going to work out to be 32 plus 16h plus 2h squared minus minus 20 minus 3h plus 6 minus 18. Okay, and so let's see here. Wait, mine's a little off. Sorry. What's that? 5h? Let me look here. It looks like my notes I kind of skipped a set, so I'm just going to do it out. All right, so 2 times 4 plus h squared minus 5. Oh, that's what it is. Okay. 5 times 4 plus h plus 6 minus, so f of 4, 16, 32 minus 20, 12 minus 18. Okay. And so this is where the 32 comes from, because 4 squared times 2. And then I have 8h times 2 h squared times 2, negative 20, minus 5h plus 6 minus 18. I think that's what I had.
Do you need to know how to do this way, or?
Either one's fine. F of x is fine. Okay, so then we have, in terms of combining our like terms, yeah, so we're going to have the constants are going to cancel. 32 minus 20 is 12, plus 6 is 18, minus 18 is gone. I have 16h minus 5h, so I have 2h squared plus 11h. I'm going to take an h out, which is the purpose. And so your h's cancel, and now we can take the limit. Which will be 11. Okay, did you not get that with the other one?
No, I don't.
What's that?
You only need to know one.
Right, but you guys got 11?
Yeah.
Yeah, okay. Should get the same thing. Everybody okay with that? Okay. So it's 11, which is all we need to know. So we figured that out, no problem. Remember that represents the tangent slope at 4. So at 4, 11 is the slope of the line that will go through that parabola. So we know this is a parabola, I hope. Okay, so 11's that slope, which makes sense because it's 4, which is a relatively big number, so it's going to be pretty steep at that point. Okay, just some other things here. So if I compare the definition of a derivative with the definitions in Chapter 1, we have the following. So interpretations of the derivative. 1, as a slope of a tangent. So the derivative puts out the slope of the tangent, which is what we just did. Right? Lesson 5. The tangent line to a curve y equals f of x, the point a, f of a, is a line through a, f of a with the slope of the derivative of a. So that we kind of say that again. So what we just did, that means 11, that was a slope. Okay? At 4. Does that make sense? The slope at 4 for that function was 11 for the tangent slope. Second interpretation for the derivative as a rate of change. So this is our velocities we talked about. Still can use that. As a rate of change, the instantaneous rate of change of y equals f of x with respect to x when x equals a is equal to f prime of a, which is the derivative. In particular, if s equals f of t is the position of a function of a particle, then v equals f prime of a. So that just means that the given time point of t, I know a lot of variables here, I know I'm getting a little bit close to Japanese, but t is your a, okay? It's like your x value, okay? So it's just saying at a specific time point, you do that derivative, it'll get you the instantaneous velocity, which is the exact same thing we do here. Okay, they're pretty much the same thing. They just mean they're the same process, just giving you different results. Like this is actually give you a slope of tangent. The definition of the slope of tangent is the rate of change for the second piece. It's just what the derivative can do for us. You're going to see the variety of things it can do in terms of problems as it works through this course, which actually gets quite interesting. Okay, so find the derivative of x squared minus 3x at any number a. Then use it to find the slope of the tangent to the parabola x squared minus 3x at 1, 2, 3, and 4. So we're going to do the same thing we've been doing. Okay, again, you can use either one. I'll go ahead and I'll just do this one. I'm going to stay with the h1. Okay, so I'm going to go, remember they say in terms of a. So we're doing a general term. So you're going to get an equation here. You're not going to get an answer. So we're going to go f of a plus h minus f of a. This is going to be quite messy. All over h still. F of a plus h, so that means a plus h squared. A plus h squared would be a squared plus 2ah plus h squared. And then the second piece of it, minus the 3x of it, would be minus 3a minus 3h. Okay, so that would just be the left piece. I'll do the right piece in a second here. Again, that's me just foiling this out. This way you get used to this pattern. The outside squared 2 times the middle. Okay, so then it's going to be this. A squared plus 2AH plus H squared minus 3A minus 3H. Plug in that minus A squared minus 3A, which would be a plus because it's minus a minus. Okay, it's all over H still. I'm going to combine like terms. Gone, gone. So that's helpful. Gone, gone. And then I have H squared plus 2AH minus 3H. They all have an H. We're happy. That's the purpose. And now we're ready to plug in the 0. So when you plug in the 0, you'll see we get 2A minus 3. See that? Because that's 0. So your answer is 2A minus 3. This represents the equation of how our tangent slopes change. This represents the equation of how our tangent slopes change. Because remember, we're talking about curvature here. We know this is a parabola, so we know as that parabola gets steeper, my tangent slope is going to get steeper as well. Okay, so he's not going to give you one answer every time. So now what we do is we plug in 1, 2, 3, and 4 to here, and it gives us the time point for that tangent slope. So for 1, it would be, so if I did, let's see here, x equals 1, we get negative 1. When x equals 1, or a, time point 1, it's negative 1. Yeah, a is x, sorry. Probably should denote that, yes. X is equivalent to a. So then x is 2. We get 1. When x is 3, we get 6, 3. And when x is 4, we get 5. Okay, so like really quickly, let me kind of explain this just in terms of visually, so you're not just writing things down and not really understanding. I know that x squared minus 3x, let's see here, that looks like this. So it's here, it's there. So it looks something like that. That's what that parabola looks like. Okay, so we think about at negative 1, or excuse me, at 1. See here, so this right here is 1. I need a negative slope to hit that, right? And then look what happens at 2. At 2, I'm on this side of the parabola, so I have to come up at it. That's why they went from negative to positive slope. So essentially that means is 1 is on the left side of your parabola. That's why it came down at negative. 2, 3, and 4 were all on the right side of your parabola, and that's why they got steeper. So we went 2, 3, and 4, etc. They just keep getting steeper as you get farther to the right of the parabola. Okay? So understanding how that's working visually. Any questions on that? What's that? We're good? Okay. All right. So the derivative as a function. The derivative function f at a, again, is f prime of a. Yes. Yeah, that equation was the equation of the slope as it changes in respect to tangent to each spot. Right, so these are 1, 2, 3, and 4. So 1 was on the left side of the parabola, so to go through that one spot, it's a negative slope. That's why that was negative. And then once I hit 2, 2 is on the other side, so now I have to go up through that. 3 I have to go up, 4 I have to go up, and that's why they're steeper, because as I get further, I have to get steeper. Yep. Good? Okay, great, great. All right. All right. Oh, it's okay. Got plenty. The derivative function again, so again, is denoted by f prime of a. But if we let a vary over the domain of f, we can change our point of view and regard f prime as a function. So given that the derivative of f is a function, f prime is defined by that there, which is what we've been using. So it's just pretty much the definition. They're really hammering home here is the understanding that the derivative is equivalent to the limit of the tangent slope. We gain the tangent slope. We're going to be doing this shorthand as we get going, but they're just really letting you know that derivative is essentially the definition of a limit. Okay. All right, so let's get going to, all right, find the derivative of the function x squared. So find the derivative of the function x squared. Pretty simple one. Just go ahead and try that really quickly. I'll kind of write it here while you're doing it. I'm just staying with h today. I don't know why I chose h, but. So this is when it just says find the derivative, it means the general, so we're not going to get a numbered answer, right? It's asking for the equation again. It's not saying at a specific time point or specific spot. It's saying in general. Okay, so we do that. So then we're going to have oh, sorry, it's f of x, not f of h, sorry, if you're following me. Okay, so then I know that these go away. I get 2xh plus h squared. They have an h in common again, which makes us happy. X is the equation of the tangent slope. 2x is the derivative of x squared. Does anybody notice a pattern at all yet? Okay, you're close. You're close to thinking about what the power rule means. That's close. Just pay attention to this. We'll come back to it on Monday. Okay, how about this one? Find the derivative of that one. It's a little uglier. Okay, radicals. You will have a couple of those in your test tomorrow, so make sure you're ready. Okay, so let's see what that looks like here. So that means we're going to have so this is where we have to use the beautiful conjugate you miss. That's a H right there for copying me. Yep, we're going to state the domains at the end. No, it's okay, but I forgot to say that. We're stating the domains at the end. We're going to see how the domains change between the derivative and the original. We're timesing this to top and bottom because it's the reciprocal, or not, sorry, it's the conjugate. So that's going to give me on the top that. The bottom we're not going to touch. Okay. So remember, I do the conjugate so that I can get rid of the radicals. And I hope that things will cancel, so I only have h's left. It does happen for me again, which is nice. I have the x and the x go, the 2 and the 2 go, so all I have left is an h, and my h cancels there. That's why we don't want to multiply the h in right away. So then we have this. and we plug in 0 for h now. You guys see why I put 2 root x plus 2? Because this 0 is gone, right? So that's an x plus 2. They have the same radicand, so that you can add them. So it's like adding a 1x plus 1x, you have 2x. So we have 2 root x plus 2s. Okay, so that is the derivative. Yep.
If you're doing it this way, what would you plug in for your for the other form?
Oh, you would have to write this whole thing. So you wouldn't put in a value.
So it'd just be, so if it's like, what do you do?
Oh yes. So sorry. The f of a1, you have to use this one because you don't have an a.
Okay.
Yeah. Good point. Sorry, I forgot. So you just ask on the f of x minus f of a. Obviously, you can't use that unless you're given an actual point. We don't have a point here, so we have to use the h, which is more by definition. Okay. Okay. So really quickly, the domains. So the f of x domain versus the f prime domain. Yep.
How did that, you get that answer?
Here.
Yeah.
So are you good to here?
Yeah, I know, but today.
Yep. So I put a 0 in for h, so that's pretty much gone.
Oh, and then,
Yeah, I got 2 of them. Okay. So go back to the original here. What is the domain for that? Just did that today in restrictions for Math 20. Yeah, it's got to be bigger than -2, right? So your domain for the first one is greater than or equal to -2. Why? Because we can have a negative and a radical. What's the domain for my derivative? Yes, it's greater than 2. Why can't it be 2? -2. That gives you a 0, correct. Correct, good. Yeah. Yeah, you can take them. I'm not done yet, but it's okay. Okay, so for example 5, go and try that one. See what you can do with this one. I will tell you this is going to take some paper, so I'll give you some time. Okay, because you got division up there. Okay.
Do you have to like put a column base or?
Yeah, so we're going to try to get these to be the same. Yeah, it's going to be, like I said, it's not going to be very pretty. Okay, so we're going to go... When you're getting a common denominator and easy fractions, if you can't get them to be the same, you multiply them by each other. You have to do that. Okay. I'm I'm only doing the tops right now. I don't need to keep writing H on the bottom, so I'm only doing the top right now.
So like, what happens to the A's? Is x equal to A?
What's that?
Never mind.
Okay. Plus x minus 2h. Say it again. I leave it till the end just to make sure. I don't do it first. Right, I'm going to simplify the top first and see what it looks like, just like we do have the H, right? Multiply the bottom last. All right, so here's my long string. So now, go through, sweet, 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 sweet. All I have left is a negative 5h.
Is that just the top?
What's that?
Just the top?
Yeah. Okay. So all that has a negative 5h. Are we good with that? Okay, so then what that gives me, got a negative 5h is all that was left on top. The bottom, we still have that h, right? From earlier. And then we still have the two things we multiplied by. Oh, sorry. That's on the bottom. Yeah, you're right. That's up here. But it slides up. So it's right there. So you're right, but I'll write it. So what Josie's saying, you're right. It's like that, but in terms of fractions, remember that's over 1, so this goes here, the 1 goes at the top, which doesn't mean anything. So that means that cancels the h's. Okay, so the h's are canceled now. We can now see if we can do the limit. Okay, so now we can see, can we do this limit? We have negative 5 on top. We have 3x minus 2. 3x, or not, see if we can do it, sorry. We're going to, yeah. We plug 0 in, so what happens, that goes away. And what do we have? 2, 3x minus 2 is on bottom. So your equation for the limit is going to be this. That is your derivative. That's what f prime is. That's your answer. All right, so we'll take questions now. So again, we didn't have a number. We didn't have a number plugging in. So you have to understand that we're going to get a function as an answer. Okay, so this is a function, so it's not a value. We have to expect that. Okay, and then our h, when I did my limit, my h went away. I had 2 3x minus 2. That's why I got 3x minus 2 squared. Okay, so if I want to figure out the tangent slope, I still would plug that in. I can still plug in a 2 here, and it'll tell me what that slope is. So, for example, this would be, if I plugged in 2, let's just randomly pick 2. 6 minus 2 is 4. 4 squared, 16. Negative 5 over 16 would be the slope of that tangent at 4. Okay, just randomly picking one. Okay, questions? Okay, so we're going to talk about it visually next, and then we're going to start finishing up here. Okay, so visually, we know the value of the derivative of f at f prime can be interpreted geometrically as the slope of the tangent line. So for example, this graph here is f of x, right? So why are these important? Okay, those are tangents, but what's the slope of those tangents? 0, right? And if the slope of the tangent's 0, what do we know about that spot? What do we know about that spot? Well, if the slope is 0 there of the tangent, that means that that spot is going to be on your graph of your... So this is a graph of f of x. If I do a graph, which is the next page, if I do a graph of the f prime of x, they're going to share that point. Because that point's unchanged. The slope is 0 there. The slope is 0, there's no adjustment, there's no tilt. It's just 0. Now these will change. Okay, so let me show you the other picture maybe. So here's them lined up. So here's 0. So let me make this a little darker. So there's this spot. And here's this spot. Okay, so at 0, what's the height here? So not the same, but what's the height? 2, okay. And then we have, and it's at -2. So what are we doing at -2? It's at 0, is my point. Sorry. So let me explain that one more time. The slope here is 0. This is a graph of the slope values. So we know this tangent slope is 0, right? Okay. This graph is illustrating the function of the changing slopes. So 0 is at 2. That's why this is now at 0 at 2. This right here is 0 at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's at 0. So again, the bottom one is the graph that represents the slopes of the tangent. This is the original. So here, they kind of, this spot right here, they're just telling you this, like just for you to kind of understand visually. At this spot, they're just telling it. This is the tangent slope, that's 1. So then you come over here, at this spot, it's at 1 for height. So again, that graph on the bottom represents the y values. The y values represent the slope of the tangent. Okay, it's just kind of showing you their relationship. Okay, so then look at this here. So right here, this spot's -1. So if I draw this red line down here, that's at -1. This spot here, 0. That's why this spot here is at 0. Where's another one? This spot here is at -2. So I go down here. That's why the graph's at -2. Okay? They just gave you these. They're just telling you these are this tangent slope that there's 1, it's 0, it's -1, it's 0, 0, -2. So if you draw a line directly from those spots straight down, that's where this graph actually is at. Okay? Because it's the output, okay? All right, so don't sweat that. It's okay on that if you're not a little confused there. You do need to know this because this will help you as things get harder. dy dx. dy dx stands for f prime of x. It's a notation that you're going to want to get to know. This means derivative, especially when we get to our second derivatives. dy dx represents derivative. Derivative with y with respect to x. That's why y is on top. We will get into a game later. We're going with x respect to y. It'll be dx over dy. So dy over dx means derivative with y respect to x. Okay, so this is what we got, guys. We did this one already, right? We figured out the derivative was 2x. So that means dy dx is 2x. The derivative is 2x. Here, we did this one already. We got that. 1 over 2x plus 2. We did this one already. dy dx was -5 over 3x minus 2 squared. dy dx means derivative. Yep. Actually, I'm not sure, but I'm assuming derivative. It's a good question. It's kind of like slopes m movement, I guess. I don't know. But dy dx is the notation we use. Okay, so then Again, back to the very beginning, they keep doing this. Derivative with respect to y to x is also the limit, the change, which we've already done. So I'm not going to go over that some more. All right, let's try to get this done here. Or actually, let's stop here. It's probably a good spot to stop, and maybe we'll finish it on Monday. Yeah.